All right, so we're going to continue talking about forces in two dimensions, and we're going to do some angled force problems and some inclined plane problems. The cables problems are going to be optional for this year. If you would like to study them independently, you may, because there are sometimes problems like them on the AP exam, but typically they are more conceptual in nature. So we will not be focusing on them due to our time constraints this year. So, as with projectiles and kinematics, we can have forces in multiple dimensions. When we had our cart tension problems, we kind of got around that by unfolding the problem. We kind of unfolded or tilted those cables and those pulleys and masses so that everything was going in the same direction. But we can't do that with every problem. So, since forces are vectors, perpendicular forces are independent of one another, so we need to remember that. Luke, remember the trig, Luke. Trust in your trig. As with other vectors, we need to resolve force vectors into their x and y components using tools like SOHCAHTOA and the Pythagorean theorem. So you can see we have this 30 Newton force vector, and it is at a 30-degree angle to the horizontal. So we can use SOHCAHTOA to find our x side and our y side. Okay, so if we have a 30-degree angle and we have a hypotenuse, the 30 newtons, we can use sine and we can use cosine to find the x and y sides, to find our x and y components. And if you don't remember how to do that, you really should by now, and you really need to review SOHCAHTOA, Pythagorean theorem, and vector math. Okay, so here's a quick example. Stan and Kyle are dragging a 50-kilogram sled across a frictionless ice rink with a force of 800 newtons. The rope attached to the sled is at a 30-degree angle. What are the x and y components of the applied force? And what is the acceleration of the sled? Okay, so we've got the sled, and we have some applied force, and it is at a 30-degree angle to the horizontal. We have, of course, force due to gravity and force normal force. Okay, so what we need to do is we need to split our applied force into its x and y components. So we have this applied force, and we know that it is 800 newtons, and it's at a 30-degree angle. What we need to find is the y and the x. That would be f sub x, f sub y. Okay, so in order to do this, we need SOHCAHTOA. So sine of theta is equal to the opposite side divided by the hypotenuse. So that would be, our opposite side would be the f sub y value here. So in order to find f sub y, we have sine of 30 is equal to fy divided by 800. So if we rearrange this equation, we have 800 times the sine of 30. And that's going to give us our f sub y. So 800 times the sine of 30, make sure you're in degree mode, is 400 newtons. So our f sub y component is 400 newtons. So I'm going to write that up here so that we can use that space again. F sub y is 400 newtons. Now let's erase this. And we'll do our x component. So if we're thinking about the x component, we have the adjacent side. So according to SOHCAHTOA, we use ka. We'll use a different color here, maybe. Green. Okay. So we know that the cosine of 30 is equal to our adjacent side, adjacent to the angle, f of x divided by the hypotenuse, which is 800. So that gives us f of x is equal to cosine of 30 times 800. So if I do 800 times cosine of 30 on my calculator here, f of x is equal to 693 newtons. So f of x is 693 newtons. All right, so we're going to erase that and look for part 2. So we've answered part 1 of the problem. What are the x and y components of the applied force? Now we're going to try and find the acceleration of the sled. So the sled is not moving up or down. It's not floating in the air. The problem's not saying anything about that, so we're just going to assume it's not floating in the air. It's not flying around. It's not sinking into the ice rink. So we have no acceleration in the y direction. So a sub y is 0. So we have 0 meters per second there, squared. Don't forget your squares. But we do have acceleration in the x direction because we have unbalanced forces. So remember, if we have unbalanced forces, we have acceleration. So we just have this applied force in the x direction. You do not want to use 800 newtons for acceleration because that is a resultant. And we're looking for the acceleration in the x direction. Ax, what is it? So we don't want this resultant because that's x and y. We want to keep things independent, okay? So what you're going to do is use f of x that you found earlier when you split this resultant into its components. So we know that the sum of the forces in the x direction is equal to the mass times the acceleration. So our acceleration is going to be fx divided by the mass. And I gave you the mass, so we've got fx at 693 newtons. The mass is 50 kilograms, gave that to you in the problem. And so we've got 693 divided by 50. That is going to be rounded up 14, oops, not newtons, we're doing acceleration, 14 meters per second squared. Let me fix that for you, 14 meters per second squared. Okay, so that's how you would solve that problem. Again, you need to make sure that you split your force vectors into the x and y components before you do any math with them, just like we did with projectiles. Okay, I'm going to clear that out here. We are going to, well, let me go back to that one. So say we have the same sled, but we have a non-frictionless surface. Now, in this case, I'm not going to do the problem for you, but in this case, we would have that same applied force, but then we also have a frictional force here. Remember that friction is equal to your coefficient of friction times the normal force. So you have everything that you need to solve this. Again, you're finding you already have your x applied. So the sum of your forces in the x direction is going to be equal to fx minus ff. You can find ff, even though I haven't given it to you, because I gave you the coefficient of friction. And you really have the normal force because the normal force is equal and opposite to your gravitational force. So you can use the mass of the sled times the acceleration due to gravity. And that's going to be your normal. You've got your coefficient of friction. You can pop all of that into your equation here. And then that's all equal to m times a. And you can solve for your acceleration. Okay, again, we're going to skip the static equilibrium cable stuff, and that homework for that section is optional because, again, we are kind of pressed for time, and that stuff isn't heavily represented on the AP exam, except in more of a conceptual way. So we're going to talk more about 2D dynamics on inclined planes. So when objects are resting on inclined planes, non-level surfaces, the normal force is not equal and opposite to gravity. You have to be very careful of that. The normal force is always perpendicular to the surface that the object is resting on. So in this case, we can see that our normal force, and it should be drawn all the way out from the middle of the box at center of gravity, our normal force is perpendicular. It should be a nice right angle. It's perpendicular to the surface. Normal force is perpendicular to the surface. Gravity is still pointed down though, so we still have Fg here. And sometimes we have a frictional force that's coming out this way. Sometimes there's an applied force if somebody's pushing this block. But it's good to keep in mind that our normal force is always going to be perpendicular, and our gravitational force is always going to be down. So what we need to do, if we're doing a problem like this, again, we have to keep everything independent. We have to keep our x and y independent. So we need to look at either the x and y components of the normal force, which would be something like this. So you'd need to resolve for your x and your y components of the normal force. And you can do the problem that way. Or we can look at the parallel and perpendicular components of gravity. This is the more conventional way of doing it because it's kind of pretending like we've tilted this inclined plane so that it's a level surface. We're kind of just pretending that it's level. Okay. So what we're going to do is we're going to split the gravitational force into its perpendicular component and its parallel component. Parallel meaning parallel to the inclined plane surface, and perpendicular to the inclined plane surface. Because that, if you tilt your head to the left a little bit, you could kind of imagine that those are, on an XY coordinate plane that is all flat. And gravity is the only weird thing. Okay, so forces that we have on an inclined plane. Your normal force is going to be equal and opposite to the perpendicular component of gravity, not equal and opposite to the gravitational force. Okay, equal and opposite to the perpendicular component of gravity. So we have this formula here. Our normal force is equal to the perpendicular component, which is equal to gravity times the cosine of theta. So we have mass times the acceleration due to gravity times the cosine of theta, which is the angle of your incline. And then we have our parallel force, which is equal to Fg, or the mass times the acceleration due to gravity, times the sine of theta. And if you're wondering where you get the cosines and the sines, review your geometry, and you can look at your, I forget all the names of these, like equal signs, opposite signs, but you can look at your relationships in geometry and determine which one should be sine and which one should be cosine. But perpendicular is cosine, parallel is sine. So we're going to look at a quick example here, and then we will wrap up. So we have a 10-kilogram box that someone has placed on an inclined plane, and this inclined plane makes a 30-degree angle with the horizontal. So I'm going to go ahead and draw that. Always good to draw pictures. There's 30 degrees. Here's my box. What is the normal force acting on the box? And what is the acceleration of the box down the incline? So I'm going to draw these forces. We have Fg. We have our normal force, Fn. We have our parallel force, and these are not to scale. And our perpendicular force. Typically, you'd want to draw them to scale, but I've got not the best tools for this right now. Okay, what's the normal force acting on the box? We know that the normal force in this case is not equal to the force due to gravity because they're not in the same plane. They're not both in the y plane. But we do know that the normal force is equal to your perpendicular force, which is mg cosine of theta. Okay, so finding the normal force, we can just do the mass, which is 10 kilograms, times 9.8 meters per second squared, which is our acceleration due to gravity, times the cosine of 30 degrees. And that gets us a normal force of 85 newtons. So that's our answer for A, 85 newtons. Okay, now we need to find the acceleration of the box down the incline. So acceleration of the box down the incline, we're going to want to look not in the perpendicular direction, but in the parallel direction, parallel to the incline, because we're looking for the acceleration with respect to that incline. So we can start this off by looking at the sum of our forces in the parallel direction. We only have one force here, and it's the parallel component of gravity, which we know from the previous slide is equal to mg sine of theta. So if we look at this, we know that the sum of our forces is always going to be equal to mass times acceleration. So now we can say that mass times acceleration is equal to mg sine of theta. Our m's cancel out, and now we can say that the acceleration is equal to the gravitational acceleration times the sine of theta. So that's 9.8 times sine of 30. And popping that into our calculator gets us 4.9 meters per second squared. So that's how you would find the acceleration for a box down an incline. These problems can get a little more tricky when we introduce friction, but just remember that your frictional force is just going to be going in the opposite direction up the incline if your box is falling down the incline. And so you're just going to have another force over here in your net force equation. So you might have your parallel force minus your frictional force. Okay? And it depends on the direction. Friction force always opposes the motion. So if you were pushing the block up the incline, frictional force would be going in the opposite direction. Okay, so that's how you do an inclined plane problem. And I think that's all I wanted to cover for you. Yep, so the next one is friction. I encourage you to do it on your own. And we've got some homework in the homework packet that will help you practice separating some of these forces into their individual components, so resolving them, and then practicing with those inclined plane problems. The readings from them are optional. It takes you to the physics classroom website, so you can do those if you would like, but you do not need to. It's just a review of what we went over here. All right, that's all I've got for you. Hopefully that helps, and let me know, as always, if you have any questions.